Back again. This is going to be episode number 39 of Learning by Doing MPI, and it's going to be part 2 of chapter 9, which is about MPI environmental management. So we're going to continue from where we left off, and we talked about the first half of this example, MPI hardware resource info, and the next thing is inquire hardware resource information. And if you remember that, this is basically again giving you flashbacks from chapter 7, which was about groups, contexts, communicators, and caching in MPI. You remember the section that we had that splitting type, and then based on the criteria for the splitting type could be also some hardware information, and you're going to see connections to there as well in a second. MPI get hardware resource info, and then you pass in a hardware info handle, and you see that it's an output, and the type of it is just an MPI info. So this is a info handle. Simply, and MPI get hardware resource info is a local procedure that returns, so it's also a local, that returns an info object containing information pertaining to the hardware platform on which the calling MPI process is executing at the moment of the call. This information is stored as key value pairs, where each key is the name of a hardware resource type, and its value is set to true if the calling MPI process is restricted to a single instance of a hardware resource of that type, and false otherwise. So the order in which the keys are stored in hardware info is unspecified. This procedure will return different information for MPI processes that are restricted to different hardware resources. Otherwise, info objects with identical key value pairs are returned. The user is responsible for freeing the hardware info. This is an MPI info handle via the MPI info free, so you got to take care of the garbage that you make. The keys stored in hardware info object have a uniform resource identifier or URI format. The first part of the URI indicates that the provider, and the second part conforms the format used in this key provider. So the key provider can be, for example, MPI : / or I don't know, is it backslash or slash? I have no idea. It's reserved for exclusive use by MPI standard. Okay. So that one is used, reserved basically exclusively by MPI standard. And this is an advice to implementers. You see that we have MPH, Open MPIs. So these are examples. We don't care about this one because this is for implementers. And going back to let me find this out. Okay, going back to this example, the second half of this example was inquire hardware resource information. So we have this hardware info handle, and then we pass it to this MPI info create, and then we pass the address of that. And then we use this MPI get hardware resource info. We pass in our info, and these are for the things that we want to basically do inquiry about. So we don't know how many key values those key and value pairs are going to be returned. So we use this n keys, and then keys can have basically MPI max info val, that amount, and values also are going to have. So these are key and values. So these two pairs should have the same sort of length. And you see that these two are basically CS strings. These are character arrays. And then we have a flag, of course. And then we use this MPI info get n keys. And then this basically gives you back the number of keys that you have. And then finally, you can iterate over each key and then use this MPI info get the nth key. And that is, you pass in the hardware info, and then this is the number of the key. And then you pass in also the key as well, which is this thing. And and then you use MPI info get, and then you use this key. So the key is going to get returned or going to get populated by this sort of function. And then you can use MPI info get, and you pass in the key that you basically got from the previous function call. And then you pass in this thing, and the value is going to get populated here. And and then if the flag, then it prints basically this process has this key, and the corresponding value to that key is basically that. So we have the rank for this process, and then the key is going to get populated here, and then finally the value of that key is going to get printed. And finally, again, we need to basically do garbage cleaning with MPI info free, and then we got to take care of that info handle. But for some reason, I already compiled this and run it. And you see that there is no information getting printed here. I don't know why. Maybe the hardware that I'm working with, the personal computer that I have, basically it doesn't work on this. If you are working with a proper cluster, then probably you will get some meaningful information out of that. But for me, in this case, this flag is not getting passed through basically. So no printf statements are basically getting printed here. Which I say, you can try this example if you have access to a university cluster, or if you are working in industry and you have access to your own sort of company supercomputer, then you can basically try this example and see what you get as an output. Okay. So, did we read these stuff? No, we didn't. Okay, we have users should be cautious when using such keys, as comparisons between different providers may not be always meaningful nor relevant. Okay, and we have the keys stored in the info object returned by this procedure can be used in MPI com split type with a split type value of MPI com type hardware guided. You remember these stuff. So this is the connection that I said that from chapter 7 we're going to have here. Whoops. I clicked on this, or MPI com type resource guided as key value for the info key of MPI hardware resource type. Okay, subsequent calls to MPI get hardware resource info may return different information throughout the execution of the program, because an MPI process can be relocated, migrated, or have its hardware restrictions changed. So notice that this is not going to be always the same, right? The next section is about memory allocation. And we do have a bunch of examples also for this section. It starts with, in some systems, message passing and remote memory access, in short, RMA operations, run faster when accessing the specially allocated memory that is shared by the other processes in the communicating group on an SMP. MPI provides a mechanism for allocating and freeing such a special memory. The use of such memory for message passing or RMA, this remote memory access, is not mandatory, and this memory can be used without restrictions as any other dynamically allocated memory. However, implementations may restrict the use of some RMA functionality as defined in section 12.5, which we haven't seen that chapter yet. Okay. The next thing is, so this is for SMP systems. You can do like, when you have some special sort of memory that could be shared between some processes that sometimes you don't even need sort of message passing, that some processes have access to a shared section of memory, and without doing communications over the network, then they can have access to each other's information. So the first routine is actually MPI alloc mem. So it gets a size. It's an input. It's a size of memory segment in bytes. That's of course a non-negative integer, and then it gets an info. You see that. So one thing which is important, the size. It says that this is in bytes, and the type of it's in MPI aint, and then the info is of course an info handle, and then we have a void star base pointer. So this is the pointer to the beginning of memory segment allocated. And that is something which is going to get populated by this sort of function, MPI alloc mem. So whatever memory you want, you pass it to the size, and then it's going to get the address of the pointer pointing to that memory segment is going to get returned into this base pointer. So there's some information about Fortran, which basically demolished them. So let's see if something interesting is here. Probably not. So I have put the sort of brackets here. The corresponding info values are implementation dependent. A null directive value of info MPI info null is always also valid. So you can pass in also MPI info null. The function MPI alloc mem may raise an error of class MPI error no mem to indicate that it failed because memory is exhausted. And then before seeing this example, MPI memory allocation, memory allocation, before seeing this in whole, let's talk about the next function because it's relevant. It's MPI free mem. and then you pass in the base pointer. So that is initial address of memory segment allocated by MPI allocmem, the one before. You pass in as an input, and then the function MPI freemem may raise an error of class MPI error base to indicate that the base pointer that you passed in was an invalid base argument. So we have a rationale here. The C bindings of MPI allocmem and MPI freemem are similar to the bindings for malloc and free C library calls. Call to MPI allocmem with base should be paired with a call to MPI freemem. Both arguments are declared to be of same type of void star so as to facilitate the typecasting. And then the rest of information is about Fortran, which we don't care about it. Yeah. So advice to implementers, I put brackets around it. So let's see what it says. If MPI allocmem allocates a special memory, then a design similar to design of cmalloc and free functions has to be used in order to find out the size of a memory segment. When the segment is freed, if no special memory is used, MPI allocmem simply should invoke malloc, and MPI freemem should invoke basically free. A call to MPI allocmem can be used in shared memory systems to allocate memory in a shared memory segment. So this is also the whole point of this sort of section. There are like 2 examples here which I didn't want to basically get into them because we already have our own example here. These things, again, we have seen them. So we have the base pointer, we have the buffer size for size of 10 integers. And then we use this MPI allocmem with the buffer size, and we didn't pass in any info handles here. We used MPI info null, and then we passed in the base pointer. And you see that this is an int star, and then yet again, we send here the address of that base pointer. So that is very important. And then we loop through that for 10 integers, and then we sort of put some information related with the rank and also the loop variable. And finally, we print. So every process basically print its own rank and sort of the information that they have in those pointers. And then finally, you need to take care of this MPI freemem, and then you pass in the base pointer there. So let's do MPI CC, MPI memory allocation. Then you run it with 8 processes, and then you see that the root process, for example, has 10 integers 0 through 9, and then every process multiplies it, by 10, and then plus the loop variable. So that's why you see that 10 through 19, and all the way for 8 processes we use 0 through 7. It's going to be 70 through 79. So very simple example showing the syntax and semantics of that memory allocation. The next section on the line is error handling. An MPI implementation may be unable or choose not to handle some failures that occur during MPI calls. These can include failures that generate exceptions or traps, such as floating point errors or access violations. It's sort of failures that are handled by MPI is implementation dependent. So depending on the library that you are basically using, either it's MPH, OpenMPI, or the one from Intel, or I don't know, IBM or whatever. Each such failure causes an error to be raised. The above text takes precedence over any text on error handling within this document, specifically text that states that errors will be handled should be read as may be handled. More background information about how MPI treats errors can be found in section 2.8. A user can associate error handlers to 4 types of objects. So this is very important: communicators, windows, files, and sessions. And all of those 4, we already basically dealt with communicators, and more specifically in chapter 7. And you remember that even in chapter 7, we skipped the information about windows, sessions and stuff like that, because we haven't touched on those chapters yet. The specified error handling routine will be used for any error that occurs during an MPI procedure or an operation that refers to the respective object. Figure 9.1 basically presents a diagram of the error handler that is invoked in different situations. So whatever information which comes in these paragraphs is basically translated in a very simple visual manner. This is a diagram deciding which error handler is being invoked. So we have direct association, and then we have indirect association, and then we have no association at all. So direct association happens for, you see that, communicators, files, windows. these are in one category, and then MPI session in another category, and then this is the deciding sort of flowchart. Is the object destroyed? If not, then we invoke the communicator error handler in the case of a communicator, or the file error handler, or the window error handler in the case that the object is not destroyed. If the object is destroyed, then we ask this question: will process model initialized? So do we have that MPI in it or not? If yes, then invoke the MPI self error handler. If not, invoke initial error handler. Then the same sort of decision model goes for a session that we haven't talked about this one yet, what a session is. And then we have indirect association via MPI message, and for MPI messages and MPI requests. And then you see that the object in this case is communicator windows and files communication initialized on. So, and then we have MPI group. Again, that's so this one, for this route, basically it takes to the same decision that if the object is not destroyed, then do this. And then if the object is destroyed, then do that. So again, for these objects of communicators, windows, files, we're going to have the corresponding communicator error handler, file error handler, and window error handler. And for the MPI group, you see that group derives from a session. If yes, then again, we ask whether the object is destroyed or not. If it's not destroyed, then invoke the session error handler. This is the case that if you're ending up with a session, if the object is a session actually. And then if the object is not destroyed, again, we go here, whether the process model is initialized or not. If it is initialized, then invoke this sort of MPI self error handler. If not, then invoke the initial error handler. And then the final sort of category is with MPI data type, MPI error handler, MPI info, and MPI operations. And then this goes through this sort of decision making mechanism. And this is simply whatever information you see in this sort of paragraph here. We're not going to go through that because we have seen the flowchart itself. So the attachment of error handlers to objects is purely local. Different processes may attach different error handlers to corresponding objects. This is also super important. So don't expect that every process is going to have, the same error handlers. Several predefined error handlers are available in MPI. So we do have some predefined error handlers. The first one is MPI error handler. Errors are fatal. The handler, when called, causes the program to abort all connected MPI processes. This is similar to calling MPI abort using a communicator containing all connected processes with an implementation specific value as the error code argument. And here you see that we have less control over this one. This MPI errors are fatal. It basically aborts, shuts down the whole thing, all the MPI processes. We have another variation, MPI errors abort. The handler, when called, so here we have more control. So this can happen for a subset of sort of MPI processes, not for all of them. So it doesn't shut down everything. So the handler, when called, is invoked on a communicator in a manner similar to calling MPI abort on that communicator. If the error handler is invoked on window, on an window, or on a window or file, it is similar to calling MPI abort using a communicator containing the group of MPI processes associated with that window or file, respectively. If the error handler is invoked on a session, the operation aborts only the local MPI process. In all cases, the value that would be provided as the error code argument to MPI abort is implementation specific again. So MPI errors return, the handler has no effect other than just returning the error code to the user. And we have seen this MPI, the usage of MPI errors are fatal somewhere in our previous sort of chapters. We can actually search for this let's see. So this is the thing that we have. Let's do this, what's it called? MPI errors are fatal. Let's see where we use this thing. So again, in the chapter for groups, contexts, and communicators, we used already this default error handler. Okay, so now this is advice to implementers. We don't care about that. It says implementations may provide additional predefined error handlers, and programmers can code their own error handlers as well. So it gives full flexibility to you. Unless otherwise requested, the error handler MPI errors are fatal is set as the default initial error handler and associated with predefined communicators. Thus, if the user chooses not to control error handling, every error that MPI handles is treated as fatal. So it's going to shut down everything. Since almost all MPI calls return an error code, a user may choose to handle errors in its main code by testing the return code of MPI calls and executing a suitable recovery code when the call was not successful. In this case, the error handler is basically MPI errors return will be used. That is this scenario, the second scenario. Usually it is more convenient and more efficient. I'm sorry. Usually, it is more convenient and more efficient not to test for errors after each MPI call and have such error handled by a non-trivial MPI error handler. Note that unlike predefined communicators, windows and files do not inherit from the initial error handler as defined in sections 12.6 and 14.7, which we haven't talked about these stuff yet. Okay. So we're not going to deal with this stuff, are we? When an error is raised, yeah, maybe we can read this one as well. When an error is raised, MPI will provide the user information about the error using an error code. Some errors might prevent MPI from completing further API calls successfully, and those functions will continue to report errors until the cause of the error is corrected or the user terminates the application. Basically, the user can make the determination of whether or not to attempt to continue when handling such an error. Okay, we don't care about these stuff. And then we move to the next section, which says an MPI error handler is an opaque object. Again, opaque object is something which you don't have directly access to it. You have indirect access to it through some handles, which is accessed by a handle. Again, this is what an opaque object is. MPI calls are provided to create new error handlers, to associate error handlers with objects, and to test which error handler is associated with an object. C has distinct type defs for user-defined error handling callback functions. I couldn't use it. That accept communicator, file, window, and session arguments. In Fortran, we don't care about Fortran. Then we have an error handler is attached to a communicator, window, file in a session by a call to MPI whatever. And that whatever is going to get filled with communicator, windows, file, or session, depending on which error handlers we are working on. And then set error handler. The error handler must be either a predefined error handler or an error handler that was created by a call to MPI whatever. This is the respective sort of window, file, or session or communicator. And the call to MPI whatever create error handler. So and this should be of course matching, so you cannot set and create something else. Like you create an error handler for a window and then you set it for, I don't know, for a file, for example, or a session. You can't do that. An error handler can also be attached to a session using the error handler argument in MPI session init. We don't need to talk about those stuff. The predefined error handler MPI errors return and MPI errors are fatal can also be attached to communicators, windows, files, and sessions. The error handler currently associated with a communicator, window, file, or session can be retrieved by a call to MPI get error handler. And then the MPI function MPI error handler free can be used to free an error handler that was created by a call to MPI create error handler, and whatever that might be. MPI get error handler behaves as if a new error handler object is created. That is, once the error handler is no longer, So let me finish this and then we're going to continue in the next episode. So once the error handler is no longer needed, MPI error handler flee should be called with the error handler returned from MPI get error handler to mark the error handler for deallocation. So if you are using an MPI get error handler, then you need to also use MPI error handler free to mark that one for deallocation as well. So this provides behavior similar to that of MPI com group and MPI group free. Okay, So these are sort of the functions that we have here for error handlers for communicators. Um, so we didn't have time to go through the codes. I'm going to continue in the next episode. So let me stop here.